Hello. A few weeks ago, I had the privilege of doing a podcast that was aimed towards eighth grade science students. And about a week and a half ago, they sent me some questions to my about my job, about space and things like that. So today, I'm going to answer these questions and just play around with Kerbal Space Program. One of the many reasons I got into the space career field in the first place. So let's start. Right now, we're on a finishing our transfer orbit to the moon. We launched from here, and now we're here. Um, the moon has captured us with its gravity and is pulling us towards it. Our periapsis is about 20 kilometers, and once I swoop around here, we will escape the moon's gravity. But we don't want to do that. We actually want to land on it with our beautiful little lander here, which I've named Blue Devil, uh, resonant with the school's mascot, and this one named Gull Lake. So Gull Lake is our orbiter, which brings the lander to the moon. Lander's gonna the lander's obviously gonna land somewhere on the moon and come back up to the orbiter, where it will take it on home. So let's go ahead and do that. So like I said, right now we're on an escape trajectory around the moon, but we don't really want to do that. We actually want to land on the moon and do some cool science stuff. So let's go ahead. This is me just speeding up the time a little bit here so we're not here forever. And what I want to do is turn my big engine here, my big thruster, away from where I'm actually going, where I'm actually headed. And the most efficient way to do this burn, as we call it, is at the perigee or periapsis, the closest we get to the moon, or the sphere of influence, being the moon. So we'll click here, select warp here, and we'll be on our way to perigee. And it's here where we will start our burn to circularize our orbit. Alright, right now I have turned my thruster on, and we are taking away that energy that we already had. So we're slowing down, taking away that energy. This is called our apoapsis here, this little tick mark, it's called a node. I want to get this to around circular, so this apoapsis is going to match our periapsis, which means we will be circular. Almost done here. Okay, the perigee is going away from us, so let me just recenter on perigee real quick. Warp to it. Make sure we're pointing in the right direction. This is just our nav ball here. We're pointing retrograde, meaning away from the direction of travel. Give it a little bit more. Alright, now our perigee is at just over 19 kilometers, and our apoapsis was really accurate at almost on the dot at 20 kilometers. So a kilometer, less than a kilometer, is really good for circularization. Okay, so I say we answer a question. The first one comes from Aiden. Apologies. First one comes from Aiden. He says, Does the ISS use solar energy to fuel the thrusters, or is the extra fuel on the station? Great question, Aiden. The fuel that is stored on the ISS is used for the thrusters. Doesn't use solar energy or anything like that. I believe they're using hydrazine on the thrusters on the ISS, and it is, yeah. To answer your question, yes, it's there's extra fuel on the station to do its station keeping. I believe they have to do about 2 meters a second per month. Great question, thanks. We actually have another station right here called Moon Lab doing some cool science-y stuff. Let's pick a place to land. I like this crater right here. I want to land... Oh... Let's pick this place. Pretty good. Might provide some good scenery, things like that. So let's pick around right there. So what we need to do... Well, we missed it, didn't we? That's not good. Good thing is we will come back around in our orbital period in about let's say, I think around half an hour, but we can warp to it. Let's do that. So what we need to do now is, well, actually, let's buy down this orbit a little bit and get a little bit closer. So let's dump this extra fuel we have just to get some more maneuverability out of our massive orbiter that we have here. So we're going to use our decoupler. Stage it a little bit. All right. And let's maneuver a little bit away from this debris that we have just created. This is one of the rocket bodies I was talking about. Now we're using something called our RCS thrusters. These little guys right here are just little thrusters, so I can manipulate my orbit in small ways, and then around objects like this if I need to, and it keeps me headed in the right direction if I need to be as well. So let's thrust up a little bit, because we're going to be going this way a little bit. All right. I actually want to bring this down to about 15 kilometers. Let's do that. That didn't take a lot, but we have to do it on the other side now because my apoapsis is still at around 19 kilometers. Let's spin ourselves around here. We'll take away our energy, slow down just a little bit, and the same thing's going to happen where our periapsis should stay the same and our apoapsis is changing. Alright, actually that's a lot better than we were before. Only about 80 meters for circularization. So great. Let's warp to my little crater here. Okay. So, in about 4 minutes, I'll be over this crater, and we have to do some things first. I don't want this orbiter to be going with us, essentially. So what I'm going to do is sort of separate here. Okay, whoa. It spun around on its own, that's alright. Got some lights on it. And we have our pilot and scientist here, ready to do some science and some flying over the moon. And we will say goodbye to our orbiter and do the same thing we've been doing, which is taking away some of that orbital energy that we already have. We'll have our nav ball up here. We're going to be thrusting away from the direction of motion. Orbiter still has that velocity to carry it in orbit, so we will just say goodbye to it. See our projected orbit going down here. Alright. Well, I wanted to be here, but I'm going here. Well, that's a problem. So what we need to do is thrust in a different direction, going, let's call it south. Anti-normal is what it's called. So we'll go anti-normal. Thruster's now pointing north. My vehicle's direction, or our pointing vector, is now headed south. So let's do that. Let's thrust a little bit to get where I want it to be. Alright, that looks pretty good. Let's warp down now. Traveling at a velocity of around 500 meters per second. We'll have to buy that down once we get down to where we need to be. Let's do another question here. Parker asked if he was asked to go up into space and work on something in space, would he be willing to go? Fantastic question, Parker. I would 100% be willing to go and work in space. That is my #1 dream, and I hope to do it someday. Thanks for the question. As you can see here, our Gull Lake orbiter is 5, almost 6 kilometers away. As we go down this trajectory here to land in this crater. Liam N asks, what does he think the projected time that we will have someone living or visiting on the moon for a longer period of time or a lunar colony? That's a great question, Liam. I think we, as at least as a nation and the world, we have had this idea for a long time, but unfortunately, we never have really gotten it done. So yeah, that's a great question. I don't really know. I would hope by 2030, maybe in 10 years, maybe longer. It's really hard to say. You know, with the Space Force, I hope we can generate some more interest in space, so we can get that done. Maybe you would be one of the first ones to live on the moon. That would be really, really cool. Another question here. Jeffrey asks, does he eat mustard? Does he eat mustard? Do I eat mustard? Yeah, I like mustard. Thank you for that question. All right, let's start to thrust down a little bit. Actually going to adjust a little bit, doing that anti-normal burn again, that southerly burn, so I can just tweak this a little bit. I want to land sort of right in there. Yeah. Beautiful. All right. Almost half a kilometer a second. We are cooking. So we got to buy down some of this velocity that we've built up. All right, not far from the surface now, about 2.2 kilometers. And we really brought down that velocity to only about 20 meters per second. But the move does have gravity, so that will increase as we try to land. So we're using our thrusters now to sort of fight that gravity. Decelerating slightly. Only about 1.5 kilometers to go. Looks like I've got a friend over here, Seeker 1. Probably a probe of something I put up here at some point. About a kilometer to go. Slow down a little bit more. Nice flat area with no debris. $500. These guys are having a great time. $300. See the shadow of our lander vehicle here. We'll slow down a little bit more. About 100 meters to go. I'm going to aim to land at about 1 meter per second. $50 meters to touchdown. $7 meters. 5, 4, 3, 2, 1, touchdown. All right. We're on the moon. Fantastic. All right. So let's take another question. Taylor asks, did you ever consider having a different career if you weren't part of the Space Force? What would be your interest? What is the most dangerous mission or experiment you have seen or been in while working in the Space Force? I will answer two of those questions. The last question, unfortunately, I will not be able to answer, although I wish I could. Um, yeah, like I said on the podcast, you know, aerospace has always been a passion of mine. Working with planes, things like that. If I weren't part of the space force, what would be my second interest? Either planes or cars. Really like working on cars. Four wheeling, going fast, modifying cars, things like that. Thanks for the question. Yeah, it was great. Kind of in the same vein, Emily E. Did you want to be something else when you were young? Yes and no. I kind of wanted to follow my father's footsteps of being a police officer, um, maybe a race car driver, things like that. Um, I also actually wanted to be sort of a movie producer, kind of kind of the thing I'm doing right now, providing a video to you guys. So pretty cool. All right, let's get out of our lander here and do some cool science stuff. Got our little astronaut here. Gonna have to let go and grab our, oops. Oh well, that's okay. She'll just fall to the surface there. All right, let's, I don't know, let's plant a flag. Whoops. The Gull Lake flag. Gull Lake landing. All right. I guess we'll take a surface sample and we will head back home. All right, so our uh, our orbiter is really far away from us. So we can do something about that. We just have to wait a little bit. So we can wait for our orbiter to come back, or we can launch now and hopefully try to catch it. But I say we should wait. So let's warp a little bit, maybe a couple hours. And it's almost to us, so I think we can go ahead and start thrusting upwards again. Let's take off. Put away our ladder, don't need that anymore. Also our landing gear. Oops, wrong way. Alright, like I said before on the podcast, not only do I have to have enough energy to go up, I also have to have enough energy to go sideways as well. Because if I went straight up, as you can see, I don't have enough energy yet to go all the way around the moon. So at our apoapsis, we will sort of do that gravity turn and start to go sideways. If I'm correct, it looks like that is Gull Lake right there, our orbiter. Let's start thrusting now so we can start heading in the right direction. Gull Lake passing over us. That's okay. We can fix that later. Apogee kind of falling away from us here just because we are um, making our orbit a little higher further away. And we just got a periapsis from coming up from the surface of the moon. We kind of want to match Gull Lake's altitude as well. So what do we have here, or what we do have here, is kind of a problem. Gull Lake's inclination over around the moon's uh, equator is essentially zero. Okay, let's call that zero. And our Blue Devil lander is not, essentially 2.6 degrees off of the equator on opposite sides. So we call this our ascending node when we're going north, quote unquote north, past the equator. We start to go up here, and then at some point we start to go down, and the descending node is when we pass through the equator going south. So something we can do about that is kind of in the same vein what I was doing when I was correcting my orbital path so I could land there. So all we have to do is either thrust in a southerly fashion at this ascending node, or a northerly fashion at the descending node. So let's do that, so we can match Gull Lake's inclination. So we'll warp there, and because we are trending north, we have to burn south. So we'll start to do that. And this ascending node is in relation to Gull Lake's node. And this takes tremendous amounts of fuel to do this in real life. Node will move on us, that's alright. And we're pretty much plane matched at this point, which makes me really happy. But the thing that doesn't make me happy is, well, Gull Lake is really far away from us. So what do we do? Well, our orbit right now is slower than Gull Lake's on average. So what we can do is slow down to speed up. Kind of a funny way to think about it, but it's something that we have to do in order to catch up with our vehicle to go back home. Like I said on the podcast, you are going faster. So Gull Lake is going faster than us right now. Its velocity is 550 meters a second. We only have 545, almost 546. It's slightly faster than us, which is a problem because as we go through these orbits, Gull Lake will only get further as us as time goes by. So we can fix that. And what we'll do here is, if you guys can make a prediction, slow down to speed up. So we're slowing down, buying down that velocity, which we're traveling in this way, pointing our thrusters in the direction of travel. I'm throttling up at this point. And as you can see, we are pretty much matched in our orbit. So we're quote unquote co-orbital right now. Let's take another question. How does it feel to fly things in space? Are you scared? Mark asks. It feels amazing. Like I said before, it's always been a dream for me to quote unquote fly things in outer space. Let me say this. Am I scared to do it? No, but it does get nerve-wracking, especially when you don't know where your spacecraft is, and that is not even uncommon, because right now this is, if we could fly things like in this video game, I know exactly where this vehicle is on Earth in front of a computer, which I am controlling these satellites. A lot of times we don't know exactly where the vehicles are, not to a very, very certain degree at least. A lot of times we can, sometimes we can't, and that's when things get scary. It's when you have that much error that you don't know exactly where your spacecraft is. So it can be nerve-wracking. Thanks for the question. Chase asks, I'm wondering how strong solar wind is, and is it stronger than the wind on Earth? Chase, great question. So when we talk about solar wind, mainly what I'm talking about is what we call solar pressure. These particles coming off of the sun, beating down on our spacecraft is very, very little. I believe it's on average between 0.5 and 10 kilo electrovolts. So that is very, 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 very tiny. So think about maybe, I think it's about 1.8 with 15 zeros in front of that foot-pounds of pressure. Not per square inch or anything, just a baseline pressure measurement. Great question, thanks. Charlotte asks, do you ever see anything that looks like an alien spaceship? No, can't say I have, although that would be very, very cool. All right, let's start to get closer to this thing. We're about 46 kilometers away, and we're not getting any closer or further from it. So what we need to do, like I said before, is slow down to speed up. All right. So I just throttled up there a little bit, and I want to use my tiny RCS thrusters to accomplish this. So a couple nodes we see here, orange and the pinkish purple. Right here is intersect 1. This is where I'm going to be at that point in time, and this is where my target's going to be. So still 47, 48 kilometers away, but I can buy that down with these little thrusters I have. Gotta watch our altitude over here. 10,000. That's really the only as far as I want to go, really. And we'll see what happens if I just leave this over time. These intersects aren't going to be true every time in orbit, and let me show you what I'm talking about. So we'll warp it a little bit. Running really low on fuel, but that's going to be okay, I think. So now I'm going faster than our orbiter here. 550 versus 560 for us. Getting a little closer here, buying down that distance. All right, see what happens here. Whoops, it thrusted on its own there. That's all right. So what will happen here is this will sort of change, and this will sort of project where Gull Lake is. This one with the dotted line here. This is where I'm going to be at this time in about 5 seconds. And watch what happens when we cross that line. All right, changed a little bit, and a lot closer than it was, well, right now. And the reason for that is I'm going to be in a phasing orbit to catch up with Gull Lake, and in about one orbit, Gull Lake's going to be here, and I'm going to be here, only about 1.1 kilometers away, and with a relative speed of 7.5 meters a second. And I can even buy that down a little further by thrusting. Let's see which way it wants me to go. Okay, so thrusting up a little bit, about 300 meters and 6 meters a second that I'll have to adjust for once I get there. So really, really close, but that's as close as I'm going to get until I do something at that point. So let's do it. So we have here only 24 kilometers away, like I said before. At our next passing for these nodes, going to be pretty close. So let's warp. Going faster than our orbiter, catching up with it. Going around the moon, pretty close, but only about 10 kilometers. We're not going to smack into it or anything. All right, only about a minute until our closest approach. So we see here, only about 200 meters. So we'll see our target here is moving, like I said before, relatively 6 meters a second away. Or right now it's going towards us. And that's the closest it's going to get right there. So now it's moving away from us. Cool little shot there. That's cool. Got the Earth in the background. All right, let's start moving toward it. Actually, let's buy down our velocity in the direction that we don't want to go in. So let's start to slow down in this direction. So I'm throttling up right now. Let's use our RCS thrusters. That'd be a little easier for visualization. And I'm currently moving towards my target, in this direction, 1.2 meters per second. So if you can see, our next closest approach, with a relative speed of 1.1 meters a second, we have a separation of 1 kilometer. So I'll want to do something in between then. Whoops. So now I'm moving our, right here, this is called our velocity vector. And the vector towards our target is represented by the pink dotted circle. So this is where we're going. This is where our target is. And the center of the nav ball here is what our pointing vector is. Let's go ahead and adjust that a little bit. All right. So right now, our velocity vector is pointing towards our target, which will eventually we'll smack into it, but we'll have to do some clever maneuvering to not do that. We're warping right now, only about 200 meters away. And over time, our velocity vector will miss our orbiter here. No big deal. No big deal. Only about 80 meters to go. Let's do the same thing, adjusting our velocity vector. Going towards our orbiter now. Only moving toward it at about 0.7 meters per second. We can speed that up a little bit. Alright, so we're at about 50 meters a second. I'm actually going to drop off the rest of my, my fuel. I'm going to back up and decouple this fuel tank and our landing legs here and our thrusters. We also have these little thrusters here so we can actually get to where we're going. So we'll say goodbye. Don't need you. Turn our lights on because we need to see. Moving toward my target at about a meter a second. Just doing some good old rendezvous and proximity operations. Alright. Let's switch to this vehicle so we can set this as our target. Just make it a little bit easier on us. Everyone working together. Actually coming in pretty good. Let me swap again. Velocity vector is a little off, so let me adjust that ever so slightly. Alright, pretty much centered. Coming on this docking port here. There goes our debris. Only about 3 meters away. And we've docked. Great. Let's go home. Alright, last question is from Michael. What is the hardest part about moving satellites? That's a great question. I would say before, just like I was talking about, not knowing where your spacecraft is at all times can be pretty nerve-wracking. Also, there's a lot to learn, a lot of software that you need to learn depending on your mission. You know, math and science can help you in a lot of ways, but you've really got to make it work for you. You've really got to learn it if you want to have a career in the STEM field. Great question, thank you. All right, let's move our guys over so they can go home. Transfer that guy over. Transfer that guy over. And, well, I guess we can say goodbye to our lander since everyone is in here. Let's just double check. Alright, got 3 of 3. We can go home now. So another interesting thing, I'm actually going to have to thrust where I just was. Oh, whoa! Don't do that. Okay, so I'm actually going to have to thrust in this direction because the moon, its velocity, its direction of travel is going this way. So I actually want to slow down, not speed up, because if I sped up, I would get a most likely a escape velocity, escape trajectory out of the our planet's sphere of influence. So what we need to do is actually slow down going this way. But we're going to speed up in relation to where we are already going. So let me just visualize that for you. So speeding up around the moon is actually going to slow us down in relation to our home planet. All right. So right now, we have a escape trajectory, moon escape. Great title for a movie, I would suppose. Once I get done escaping from the moon, I will be under the influence of our home planet here, and this is what my trajectory is going to look like afterwards. So right now we have a periapsis height of around 60 kilometers, and that will bring us down into the atmosphere, and we'll have some atmospheric effects on our spacecraft as well. So that's pretty cool. But I think we should just go for it and go really low and have the atmosphere slow us down and hopefully land safely. So let's warp for the last time. Say goodbye to the moon. There's the Blue Devil right there in that square. This is 50 times speed. Okay, we have just escaped the moon's gravity and are now under the influence of our home planet's gravity. Coming in pretty hot here at around 3 kilometers per second. Here on Earth, that's around the same speed as a geosynchronous satellite. Or I think nearly as fast as one of the SR-71 Blackbirds. Pretty cool jet. If you have some time, I would recommend looking it up. And this atmosphere is going to start around 70 kilometers. So almost there. Once we get there, our looks like it's already happening. Solar rays are going back in. Let's put our rear end away from the particles, as you can see here. All that friction from the air molecules. Let's see if this is going to put us. Might put us. Might have to do another round of this, but we'll see. A little overheating on our engine here. And our fuel tanks. So let's go ahead and jettison those before they get too hot and explode. Alright, now we have this heat shield here. Very, very useful. It looks like we're going to have enough friction to slow us down on our own without any thrusters or anything. down for a nice night landing, possibly in this desert area here. Pretty cool. There goes our debris. That'll fall back to Earth. Not sure if I'm going to land in the desert or not. Doesn't look like it. So we'll go ahead and pull our parachutes. Nice sunset going there in the west. Might land in the water. That's okay with me. And there's our destination in the distance. Splashing down at around 21 hours. Very nice. Alright. Thanks for joining me today. Thanks for your questions, and go Blue Devils. Thank you.